Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and in this video we are going to solve a gate question. It was asked in the 2020 year for 1 mark. So basically this question is related to process state diagram. So the life cycle of a process that we just studied in the previous video, it is about that, right? So let's go over this question. So question says that consider the following statements about process state transitions for a system using preemptive scheduling, right? So these are the given statements, and the question says that which of the above statements are true. So you are given a bunch of statements and you have to identify which of them is true. So before we go over the statements, the very first thing that we should pay attention to is that it is given that this is a system where the operating system follows a preemptive scheduling policy. So although we haven't talked about what is preemptive scheduling, it is very easy to understand, right? So I will explain you that, and this preemptive scheduling policy we will study in great detail in the upcoming topics. But for now, basically, first of all, let's understand CPU scheduling. So we know that in the modern computer system, the number of CPUs is very limited, and the number of processes that want to run on these CPUs is way more than the number of CPUs, right? So in order to deal with this problem, what the operating system does is that we know that it shares the CPU time among all the different processes that are there in the system. And in this time sharing, the operating system has to decide to which process should the control of the CPU be given to. And once that decision is made, then it has to give the control of the CPU to that particular process. So this is called CPU scheduling, where the operating system takes the decision of to which process should the CPU be assigned, and then giving it the control. So now we understand the CPU scheduling part. So let's talk about what is a preemptive scheduling policy. So basically, when the operating system is performing CPU scheduling, it has two options. In the first option, that is preemptive scheduling, it can forcefully take the control of the operating of the CPU from a running process, right? So let's say there is a process which is running on the CPU, its instructions are being executed on the CPU. Then, if the operating system has the capability to take away the control of the CPU forcefully from the running process, then it's called a preemptive scheduling policy. And the opposite of this is the non-preemptive policy, where the operating system cannot take away the control of the CPU forcefully from the running process, right? In this non-preemptive scheduling policy, the process will voluntarily give up the control of the CPU. Then only the control of the CPU is transferred to the OS. It is never forcefully taken away from the running process. But in this question, we are given that the scheduling policy that the operating system follows is preemptive in nature, right? So the operating system has the liberty to take the control of the CPU forcefully from the running process. So having understood preemptive scheduling policy, let's now go over these statements and verify whether they are true or not. So the first statement says that a running process can move to ready state. So we have to verify whether this is correct or not. So if you look at the process state diagram, then this transition that is there, right? This which one is highlighted. So this transition, we can say that, okay, a running process can move to a ready state. And this transition is very important because the absence or presence of this transition signifies whether the scheduling policy is preemptive or not. If the operating system is following a scheduling policy which is preemptive in nature, then it is allowed to forcefully take away the control of the CPU from the running process, right? In that case, when it does that, when it takes away the control of the CPU, in that case, the process which was in the running state, it will go to the ready state, right? So this transition is very important in this sense. If it is present, then you can confirm that the scheduling policy that the operating system is using, it is preemptive in nature. And on the same grounds, if this transition is missing in the process state diagram, that means that the operating system cannot take away the control of the CPU forcefully from the running process. So in this case, this is a non-preemptive scheduling policy. Since is in this question we are concerned with preemptive scheduling policy, this transition will be present, and the first statement is true, right? A running process can go to the ready state. So let us look at the next statement, the second statement. It says that a ready process can move to a running state. So we have to say whether this is true or not. As you can see in the process state diagram, right? This transition, there is a transition from the ready state to running state, and this is quite obvious, right? This is obviously true. So a process which is in the ready state, the operating system can pick any process from the ready state and assign the CPU to it. And in that case, we say that the process has been scheduled to run on the CPU. So when that happens, it starts running and executing instructions on the CPU. So this statement that a ready process can move to a running state is true irrespective of whether the policy is preemptive or non-preemptive. This is true for all kinds of policies. So let us look at the next statement. It says that a block process can move to running state. So it is asking whether a process which is in the waiting or block state, can it directly go to the running state? So if you look at the process state diagram, there is no direct transition from the waiting to the running state. So this statement is actually false. So let's understand why. Because a process which is blocked or is in the waiting state, it is waiting for a particular event to happen. Only when that event takes place, right? Only when the event for which the process is blocked that takes place, then only it will be ready to execute instructions. Before that, it cannot even execute instructions. So the operating system does not allow processes which are in the block state to be assigned the CPU. That is, even if the CPU is assigned to such a process, it won't be able to execute instructions. So it forbids any waiting process to directly go to the running state, right? So it has to first of all go to the ready state. That will only happen when the event for which that particular process is waiting or blocked upon happens. And from the ready state, when it gets scheduled by the operating system, then only it can go to the running state. So there is no direct transition from waiting to running. It has to go via the ready to then to the running state. So the final statement is that a blocked process can move to ready state, whether this is true or not. And as we can see from the process state diagram, there is a direct transition from the waiting state to the ready state. So this statement is true, that a process which is blocked or is in the waiting state can move to the ready state. And this will happen when the event for which that particular process is waiting for that happens. So for example, if a particular process is waiting for an IO operation to complete, so when that event finally completes, then that blocked or waiting process can move to the ready state. So this statement is true. So now we have found all the correct statements. So 1, 2, and 4. The third statement is false. So 1, 2, and 4 are correct. So option C is the right answer in this case. So guys, this was it for this video. Thank you very much for watching. I'll see you in the next video. Thank you.